What's up, you pussy ass pussies? My name is Flynn Wilson, and this is the Flynn Wilson fucking podcast. Let's go. What does that remind me of? Let's go. What's that from? Who knows, but let's do some studying. Today is the 30th of October. Dude, exams are in like a month. I gotta list my bike soon as well. Probably do it like midway through November. I'm falling in love, falling in love. I'll do it like the same time I list my PS4. What the fuck is going on? Writing down my Feynman technique, little notes, little bullet points that I can go over afterwards. Getting my studying down. Next year is gonna be fun. Next year is gonna be fucking, oh my goodness, gonna be very fun. And it's called Black Magic. Dude, doing this podcast just gives me energy, man. I'm falling in love. Feel like I lose my charismatic self sometimes, man. Like, I don't know, sometimes, like, lately I've been having, like, an identity crisis, you know? Mainly just yesterday. Your disc is almost full. Fuck. This is fucking photo booth. Fuck, that's bad. Okay, I gotta upload some of these videos to the tube. Mainly just these fucking videos, because they're very large in size. I will start uploading these. I don't even know if it'll probably just shut off if it gets completely full. I don't know. But like, I feel like I go into a conversation knowing how charismatic I'm gonna try to be, you know? Whereas other times I'm going into a conversation, there's some pretty fucked up shit as well, which is what scares me. I go into a conversation just trying to survive that conversation, just trying to get something, like at the gym yesterday. This is where it all started. This is where I started having this identity crisis, man. Gym yesterday, I went up to this chick, and I wanted her to record a set for me, because my deadlifting form, I don't know, I just started doing deadlifts like pretty recently, so it's not the best. Trying to keep like my back straight, but it's hard to do when the weight is increasing. So yeah, I asked her to record a set. She like took out her headphones. She was like, I was like, "Can you record a set for me?" She was like, said some dumb shit like, "Oh, you know, that was ballsy to ask, so yeah, I will." And it's like I went into that conversation just thinking that this is like very transactional. Like, I just want this person to record a set. And I didn't crack a little dub. I could have cracked some little dubs there. But I didn't. What the fuck is my drink bottle? And I didn't, you know? And I didn't feel like I was being myself. I was just like flabbergasted, didn't know what to say, you know? You know? And that's because I went into the conversation thinking that this is all that's going to happen. I'm going to give my phone to this person. She's going to record a set. And I felt like I wasn't being myself there, you know? But then I started thinking, what the fuck am I? Is that me? That boring fuck that doesn't crack lol dubs? Or is the guy that actually does crack lol dubs? Is that me? I don't want it to be that way, you know? I don't want to have to consciously think like, okay, just be yourself. Don't be fucking boring. A-level physics online.
I have here a battery, which is my source of EMF. It's the thing that provides the energy for a circuit. Now, if, for example, you had a hacksaw, a bit of spare time, and this is something I don't recommend you do, what you can actually do is look inside one of these big units. And if you do that, what you can find is inside this battery is a number of cells. Now, basically one end is connected to the negative and one is positive. And if we look at these individual cells that make up the battery, we can maybe look at the various chemicals that these are made out of. Now, if we think about these chemicals, because there's a difference in electrical potential between one end and the other, we therefore have a source of EMF. And it's this kind of chemical thing here, this kind of the different layers of chemicals and their difference in electrical potential, which drives the electrons around the circuit. And this video here is really where we explore about what happens inside the cell and something which we call the internal resistance. So here we have my cell, and effectively every time that we have a current moving through this cell, what we're doing is it's basically got to move through a load of stuff. The electrons, they don't just get from one side to the other, and therefore this cell has its own internal resistance. Now we can draw that as basically a cell that looks a bit like this, and what it has is its own internal resistor. Now, effectively what we have here is this whole thing here represents my normal cell. And
this is fucking boring. EMF is the energy per coulomb produced by the battery. This is the reading of a voltmeter connected across the battery when no current is drawn from it. Terminal potential is the energy per coulomb delivered to the circuit. That is a reading of a voltmeter connected across a battery when a current is drawn from it. That is, a component is connected across it. What the fuck? Now, a Deal battery has no internal resistance. In reality, no such battery exists because all batteries contain conducting materials that provide some resistance to a current flow. A real battery with internal resistance is shown by an ideal battery. The one with no internal resistance, in series with a small resistor, are, as shown on this diagram. That's how you show an actual battery. The data box shows that the battery and the resistor are a single unit. Yes, sir. Internal resistance formula. Not all of the electrical energy supplied to a charge by the chemical reaction of the cell or battery is transformed into useful energy in the external circuit. A certain amount of electrical energy is converted into heat by a power source or battery due to its internal resistance, so less energy is available to the external circuit. What the fuck? Right. What the fuck is going on right now? Alright. We're falling in love, falling in love. Falling in love, falling in love. Boo doo boo doo. Boo doo boo doo. Boo boo doo boo doo. Doo boo doo. Boo doo boo doo boo doo boo doo boo. Dude, why are my teachers so fucking useless? Okay. Oh, what the fuck? Oh, for fuck's sakes. Oh, dope. Okay. The precise way to measure the EMF of the battery is to get a series of values for the potential difference between its terminals for different magnitudes of current, and then, dude, I don't give a fuck. Oh my god. By extrapolating the graph when the current is zero. What the fuck, man? The internal resistance of the cell is equal to the gradient of the line. EMF is the terminal voltage when the power supply is not connected into any external circuit. Every power supply has internal resistance. Yep, when a current is drawn from the power supply, there is a potential difference across the internal resistor, so the terminal voltage drops. Fucking amazing. Internal resistance, every battery has internal resistance. EMF versus terminal potential. Fuck, what was the difference again? Terminal potential is how much voltage comes back to the cell, whereas EMF is how much voltage is produced by the cell. Alright. Let's fuck around for 8 minutes. I'm falling in love. Falling in love. Because I'm falling in love. Where the fuck is my phone? I genuinely do not know. Where the fuck am my phone? Get a large fries. Vegan, please, so don't put no cheese. Just a little
mustard on the side. I'm
dumb
at
as shit.
Burger King with my Burger Queen. Can I get a large fry? She's vegan, please, so don't put no.
Courtesy shuttle that runs every 20 minutes.
What?
If you ride dirty, shout it, make sure that you ass on my tags. They inspire cause I'm stuck in 95. Oh, I got a old school Chevy truck, can't catch me cause my ride gone.
Metro boom and make it boom. Metro boom and make it boom.
The other day, Brittany and I found a beach with water so clear, that it looked like we weren't even underwater. And there's something that's just so magical about the sand here. And there's even these little barreling waves. Over the last year, I realized that I want to dedicate my life to cleaning the ocean, one piece at a time, like this soda can lid. But for the last 10 months, I felt so betrayed by a community that I thought I was a part of. All I want to do with my platform is help clean the ocean, and I feel like I'm being told that I'm not allowed to do that. What's so wrong with me that I'm not welcome here? Well, I've had enough. If you want to see where I'll be posting...
The fuck is going on?
Yeah.
Did you know that if your large katana arrives broken, we'll give you our firstborn child?
No, we're not doing that anymore. You either get a refund or a new katana.
Oh, okay. Yeah, that was a limited promotion. Well, the next step is we contact UPS and demand reparations for them ruining our lives. Then they usually give us a check and make things right in the world for now. Did you know that if your large katana arrives broken, we'll give you our firstborn child?
No, we're not doing that anymore.
Better ingredients, better pizza. All right, hold up. I'm just a pizza guy. Oh, no.
Honey. Aww. Thank
Hurry the
you.
fuck up.
Okay. Are you opening the door for me? Aww. Aww. Thank you.
Wait, you did a face reveal yesterday? Yep, I did. Aw, did I miss it?
Wait, you didn't know one got pop quizzes. I didn't know you gave pop.
Is this fast enough now, or do you want faster?
My boy Joshua. Why are you so excited?
We're gonna go watch Star Wars.
We about to watch. Oh, sorry. You're jumping on the popcorn. We are about to go watch Thor. My boy Joshua. Why are you so excited?
We're gonna.
I can't handle it. Uncle, I can't.
That's so dumb.
These Samsung cases clip on.
Yo, what's up, dude?
Yo, what's good, bro?
Wait, so
He got caught kissing his sister on the bus.
Sweet old Alabama. Yeah, shut the fuck up.
He got caught kissing his sister on the bus.
Sweet old Alabama. Yeah, shut the
Sweet, oh man.
Yeah, can I just get $2 on pump 5? Why are you laughing? Nothing. I've just never seen someone put $2 worth of gas. Broke bitch. What was that? I just don't think you deserve to own a car. Shut the fuck up. You work at a fucking gas station. You get 0 bitches. I should knock you the fuck out right now. Now you better not charge me for shit, or else I'm gonna take that gas pump and shove it up your. Yeah, can I just get $2 on?
Alright. This isn't the best study, but you know what? It is what it is. It is what it is, man. I need something to arrive in the mail today. If not today, then tomorrow, maybe the next day I'll wait, and then I'll message them saying, where the fuck my shit at? You pussy. Kirchhoff's laws apply to all circuits, including those with multiple loops. I really regret fucking deleting all my emails, to be honest with you. Kirchhoff's laws apply to all circuits, including those with multiple loops. Watch the following video. Alright, I will. 11 minutes. Fuck it. We watching this video,
Okay,
pussy?
in today's video, I'm going to go over a nice, quick, clear, concise explanation of how we apply Kirchhoff's circuit rules to determine the direction and the magnitude of the current in the branches in a little bit more complex circuit. Now, as I said, we're going to be doing this to find the currents, but you could, of course, also be asked to find the voltages or the resistances. Now, in order to get a good feeling for how these rules work, you really need to do a few problems and work on a couple examples. I will put links to example problems that you can use to practice Kirchhoff's rules, the application of the rules, in the description of this video. So please check those out. Watch this and then do a couple example problems and you should be set. Okay, here we go. Now, before we actually get to applying the rules, there's some terms you should be aware of, really just two terms. One of the terms is either junction or node. I like to use the term node. Some people say junction. I've heard people say branch point. Node. A node is a point where two or more wires are joined or two or more wires come together. And you can see in this circuit we have node number 1 and we have another node down here. This is the place where the wires come together. Now the branch is a path that connects two nodes. And we have 3 branches. We have this branch that connects these 2 nodes. We have this branch that connects these 2 nodes. And we have this branch that connects these 2 nodes. So please be aware that you should know what a node is and be able to identify the nodes, what the branches are, and be able to identify the branches. These are the steps. I would say there are 5 steps to applying Kirchhoff's rules. The first 3 are really things you do before you apply the rules. Step 4 and step 5 are applying the current and the voltage rule. The first thing you should do is label the nodes. Identify and label them. There's 1.
Bang.
We'll call that N1.
1.
There's that one. We'll
2.
call that N2.
Bang, just 2. Easy.
Now, the next thing we're going to do is we're going to assign a current and a direction of the current in each branch.
Negative. Bang. Well, they go in the opposite direction. That's not good. They cancel each other out.
I would like to say quickly that the direction we choose is completely arbitrary. When we calculate the currents, if we get a positive answer, we'll know we chose the correct direction. If we get a negative answer when we calculate the current, it doesn't mean the current is negative. It only means that we chose the wrong direction for the current. So I have 3 branches. The first branch, I'm going to say, is this one on the left-hand side. That has a current, which I'll identify as I1, and it's basically going clockwise. The second current, I2, we'll say goes from top to bottom between these 2 nodes. The third current, I3, goes on the right-hand side here, and it flows counterclockwise.
What the fuck?
Excuse me.
It's just so loud.
Flows clockwise in this direction also. So we have current 1, current 2, and current 3. Each current, or each branch has a current. Now, before we go on, I just want to say that when we apply Kirchhoff's rules and the current, what we're finding is the conventional current, which is the flow of positive charge. The electrons actually flow in the opposite direction, but this is for conventional current, which is the flow of positive charge. Okay, these are the 2 things we did so that we can apply the current rule. Now we have to do one thing so that we can then apply the voltage rule. We have to indicate the direction that we will be going around each loop when applying the voltage rule. Now, the easiest thing to do, I think, is to just choose clockwise and clockwise. We have 2 loops. Loop 1, we're going to go around clockwise. Loop 2, we're going to go around clockwise. We could also say all the way around the outside is loop 3, but for this video, we're just talking about loop 1. in loop 2, and we're going to do them both clockwise. Now, once again, when you assign the direction of the current, it's arbitrary. When you assign the direction that you're going to go around each loop when applying the voltage rule, it's also arbitrary. I chose clockwise and clockwise. You can choose counterclockwise for both of them. You can choose one counter and one clockwise and one counter. It doesn't matter. It'll come out in the math when we get the sign of the current. Okay? Okay, step 4 is we're going to apply the current rule. And then step 5 is we're going to apply the voltage rule and use V equals I times R at each of the resistors. Okay, so steps 1 through 3 are really the things you do before you apply the rules, and then you apply each of the rules. And now in the next slides, I'm going to go through some particular things you need to keep in mind when you apply the current rule and when you apply the voltage rule. Okay, this is for the current rule. Kirchhoff's current rule says that the sum of the currents at any node are equal to 0. This says the sum of the currents is equal to 0, and this is something you should be a little bit familiar with when you've talked about just regular old parallel circuits. The sum of the currents at any node is equal to 0. That means if we sum up these 3 currents, because here's our node, we have 1 current in and 2 currents out, they have to be equal to 0. The current that comes into the node is commonly designated as positive. The currents that leave the node are commonly designated as negative.
Right.
So when I sum up the currents for this node, I could write down that I1, which is positive, minus I2 minus I3 equals 0. This is the sum of the currents into the node.
Yep.
The sum of the currents at any node is equal to 0.
But they're all positive.
Now, you will often hear people say that the currents into the junction are equal to the currents out of the junction. That means the current in is I1, the 2 out are I2 and I3, and we could write down that I1, the current in, is equal to the currents that leave the junction, I2 and I3. Now, this equation and this equation are the same equation.
Mm-hmm.
I could simplify this, or if I just move I2 and I3 to the other side, I would get that I1 equals I2 plus I3. Okay, so there's kind of 2 different ways you can think about it. The sum of the currents is equal to 0, or the currents in are equal to the currents out. Okay, that is how you apply the current rule for Kirchhoff's laws. Okay? Now, there are 2 things we need to be aware of when we apply the voltage rule. In both cases, it says the sum of the potential differences across all the elements in a loop is equal to 0. The sum of the voltage drops and gains is equal to 0. This is the cross the battery convention. We're going to have batteries and resistors in this video. Okay? Now, across the battery. If, when we go across the battery, we go from negative to positive, that's a potential increase. So if we had said that we're going to go around this loop clockwise, we would be going across the battery in this direction. That means we would have a voltage gain, and we would write down plus 5 volts. Now, if we had chosen to go around this loop in the counterclockwise direction, then we would be going across the battery in this direction when we sum up the voltages. And we go from a positive to negative, from a potential high to a potential low, then we would write down negative 5 volts. So you have to pay attention with the direction you're going across the battery, whether it's a potential gain or potential decrease. All right? That is the battery convention. Now we have the resistor convention. Now this one looks a little bit more complicated, but it's basically the same thing because it's also Kirchhoff's voltage rule. The sum of the potential differences across the elements in a loop is equal to 0. The sum of the voltage is equal to 0. This is the resistor convention. We're not going to a resistor convention, but this is the resistor convention. Okay, now we're going to use V equals I times R. Here is, I indicated the current direction we chose for this branch. Now, once again, if we go around this loop in the clockwise direction,
what's going on?
We would be going across the resistor in this direction.
Okay.
That means we would be going with the current. When the current flows through the resistor, it loses energy. And therefore, the potential difference across this resistor is equal to the current times the resistance. And we say that it's negative. The current times the resistance, I times R. V equals I times R, Ohm's law. So, but we put a negative sign because we're going with the current in this case, and therefore there's a potential decrease. Now, if we had chosen in this loop to go in the counterclockwise direction, then when we go across this resistor, we would be going in this direction, which is against the current or upstream. When you go against the current or upstream, then you have a potential gain. So now it's the same voltage, but the sign is going to be opposite. The magnitude is the same. Once again, it's going to be V equals I times R, but it's going to be positive because we're going against the currents. We have to remember, if we go against the current when we go across a resistor, we put a positive sign. If we go with the current when we go across a resistor, we put a negative sign. But once again, this is V equals I, the current times the resistance. Now you'll notice I didn't use the units because there's a lot of numbers and symbols and things like that. It's usually cleaner and easier if we just drop the units and we don't use the units. Okay? So please be aware of your negative and positive signs. Please remember those 5 steps. Please remember there's the current rule and the voltage rule. If you follow those 5 steps and you apply the rules consistently, you can solve these problems pretty straightforwardly once you get a hang of how to do this. Okay, I went through an explanation in this video. As I said in the description.
Man, I really wasn't listening to that video like you. Let's listen to the fucking other one then.
Okay, in today's video, I'm going to go over an example of how we apply Kirchhoff's circuit rules or circuit laws to determine the magnitude and direction of the current in the branches in a little bit more complex circuit. In a previous video, I made kind of an introduction explanation video of what Kirchhoff's rules are, how we apply them, some things we need to be aware of when we are applying them. And I've also made a couple of example videos, which you can link to all of those videos in the description to this video. Okay, here's the circuit we're going to use for this video. We have a 3-volt source, a 12-volt source, a 75, and a 125 ohm resistor. We're going to determine the direction and the magnitude of the current in each of these branches. Okay, step number 1 is to identify the nodes. So we have 2 nodes. We'll call this one N1, and what the heck we'll call this one N2. That's step 1. Step 2 is to identify the current and the direction of the current in each of the 3 branches.
Okay, apparently you can just say fucking and just go whatever fucking direction you want. I thought the fucking cell, that the long line is the positive and the short line is the negative. And it goes from negative to positive. But because we're doing conventional current, it's going positive to negative. So you have to go from the big line all the way to the little line. But they do it whatever the fuck they want. Just do it fucking clockwise. Fuck it. Who the fuck cares?
In this circuit, we have 3 branches. Okay. We'll say that I1 flows in this direction through this branch.
Yeah, clockwise.
In the clockwise direction. I2, the current through that branch, will designate I2. It flows from N1 to N2. And the other current is I3 and also flows clockwise around that branch. Okay? Now, I want to point out that the direction of the currents that I chose for each of the branches is completely arbitrary. It doesn't matter what direction you choose. When we calculate the currents, it'll all work out in the math. When we calculate the currents, if we get a positive answer, then you'll know you chose the correct direction for the current. When you calculate the current, if you get a negative answer, then you'll know you chose the wrong direction for the current. The current's actually flowing the other direction. You'll see that in this video. Okay, that's step 1. Step 2. Step 3, so we can apply the voltage rule, is we have to determine in which direction we're going to go around each of the loops when we apply the voltage rule and sum up the voltage drops and the voltage gain. And I'm just going to say we're going to go around this loop like this. In the clockwise direction, we're going to go around this loop also in the clockwise direction. We also have this outer loop we could call loop number 3, which we don't need for this video. So we're not going to do that one. But once again, we have 2 loops. And I've chosen both clockwise, and again, it's very arbitrary. You can choose them both clockwise, both counterclockwise, one clockwise, one counterclockwise. It doesn't matter.
Okay, shut the fuck up. Go on.
Okay, that's step 1, 2, and 3. And the next step is to actually apply the current and the voltage rule, and we're going to apply the current rule at N1 and also at N2. The current rule says that, for example, at N1, the sum of the currents into the node, are equal to the sum of the currents leaving the node. Right, so we're going to say we have 1 in and 2 out. That means we have I1 positive, that's the one coming in. The 2 leaving, that's a negative. So we have I1 minus I2 equals I1 minus I2 minus I3 equals 0. Now I can solve this equation, get rid of negative signs, and I can say that I1 equals I2 plus 3. The sum of the currents in, there's only one, equals the sum of the currents out of the node. We'll do the same thing in I2. We have two currents in, I2 and 3, and I1 comes out here, plus I2 plus I3 minus I1. Solve again for I1, and you'll notice we get I1 equals I2 plus I3. You'll notice that all four of these equations are really this equation and this equation are the same equation. We only need one. We only do use the equations when we have a different equation in each node. So the same equation, we're just going to use this one equation for our current rule. Now, we're going to go around and sum up the voltage drops and the voltage gains, apply the voltage rule for each of the loops. That's loop 1 and loop 2. We're going to do that with the assistance of Ohm's law. This is where Kirchhoff and Ohm work together. Okay, for L1, we're going to start here in the upper left-hand corner. There are no elements in the first part of this branch. When we come down through this branch, we encounter this first resistor, 75 ohm resistor. And you'll notice when we go clockwise around this loop, we're going with the current. That means that the voltage is going to be a voltage drop. Now the voltage, we don't know the voltage, but we do know that V equals I times R. We know the current is I2, the resistance is 75, so we're going to write down that the voltage is minus 75 I2. It's minus because we're going in the same direction downstream with the current. Okay? And that's a voltage drop. Now we go through the bottom, nothing. We come back up here, we encounter this 3 volt source. We're going from the negative to the positive terminal. That's voltage gain, so we write down plus 3. We come back to where we started, equals 0. So those two elements, sum them up, equal to 0. Now we're going to do the same thing for L2. We start here, nothing in the first part of this branch. Now we come down here, we encounter this 12 volt source. We're going from the positive to negative, so that means that's minus 12 volts. Now we encounter this 125 ohm resistor. You notice once again we're going with the current, I3.
Minus 12.
So that's going to be a voltage drop again. So it's going to be minus 125 I3. The voltage is the current times the resistance. Now we go across the bottom, and then we come back up on this side. And now you'll notice when we go through this 75 ohm resistor, we're going against the current. We're going upstream, so to speak, against I2. That means that is going to be a voltage gain. We designate that as a voltage gain, and that is plus 75 I2. That's the last element, and we say equal to 0. Okay, so once again, I just want to point out that for the first loop, we came down this way with the current that was minus 75 I2. For the second loop, we were going in the other direction, went against the current. That's why this is positive 75 I2. Okay? You have to keep your positive, your negative sign straight. Be very careful. Okay, you'll also notice that I didn't use my units. I didn't put down volts and amperes and
I2 equals
ohms
25.
and things like that. There's enough symbols and things like that. We usually leave those off. It makes it look cleaner. We know when we do this, if we apply the rules correctly, we'll get an answer with amperes. Okay, so now we have our 3 unknowns, I1, I2, and I3.
And I2 is really
We have 3 equations, 1, 2, 3, and we can solve for each of the currents. This basically becomes now an algebra exercise, basically. Okay, what are we going to do? We have 3 equations. This equation, L1, you'll notice only has 1
over 25
variable in it, I2. So we can solve this very easily for I2. We can say that I2 is equal to minus I3 because we subtract minus 3 because we subtract 3 from both sides, divided by minus 75, and we get that I2 is equal to 0.04 amperes. Now we know I2. We can substitute I2 into this equation and solve for I3.
That's just 3.
So that means that the equation now becomes minus 12 minus 125 I3 plus 75 times I number 2, which I2 is 0.04.
Needed.
And then we get that minus 12 minus 125 I3 plus 3 because 75 times 0.04 is 3. Now we can solve for I3. Move our constant to the other side. We get 12 minus 3. Add 12 and subtract 3 from both sides, divided by minus 125. We get that I3 is equal to minus 0.072. The magnitude of the current is 0.072. This negative sign tells us that for I3, we chose the wrong direction. That's what this negative sign doesn't mean. The current is negative. Doesn't mean that the current is less than 0, obviously. It just means we chose the wrong direction. So I'm going to take those 2 arrows out and replace them with the arrows pointing in the correct direction, and that is the direction that I3 actually flows in this circuit. Okay, like I said, don't forget your negative signs. Okay, now we know 2 and 3. Now we can solve for 1. We get that I1 is equal to 0.04 minus, don't forget your negative sign, 0.072, and I1 is equal to 0.032 amperes.
How is that negative?
And that means that we have a negative sign here also again. And once again, a negative means we chose the wrong direction for the current, so I'm just going to change the direction of the current for I1 also. And there you go. That's the directions and the magnitude of the current. I1 is 0.032 amperes and flows in the counterclockwise direction. I2 is 0.04 amperes and flows from N1 to N2. I3 is...
Finally, I get to relax, huh? Is that the last lesson? Hey, it was. Dude, I need fucking Sarah to give me... Stop being a lazy fuck. And anyway, this is the end of the podcast. See you later, guys.